Eung Jin Chun from KIAS, and he will tell us about where to ski and oh sorry, different. You changed the title. It's about the Axion. Okay.
Thank you. So you mean so I don't have to speak about physics, right? But without speaking about physics, you cannot justify how to ski. I mean, so first spend a few minutes on this old topic on action physics, and then take more time for next activities. Okay, so I hope you will not be bored of this kind of old physics of actions. You know, recently there has been some revived interest in this topic because of fuss of bicep 2. And then there's another reason why, in particular in Korea, so we will have a new Axion lab, which will be taking data, I think, 2018, if they are successful. So, okay, so I present basically two ideas on Axion CDM. Two new. It's not the idea is not new, but there's again some new aspects which could be interesting. So first, I will give some short introduction to the Axion, and then probably on the first day, Yang-wan also talked about it, so I'll be very brief. And then also another short review on astral and cosmological properties of Axion. And then I'll present two new ideas on how to evade the conventional cosmological constraint of Axion CDM. So basically, I was gonna talk about this work in progress. I suppose that we were able to finish it by today, but it's far from being finished. It's really in progress. And then, furthermore, the idea may not work. So I hope any of you can find some loopholes of these ideas. Okay, so strong CP problem, we know that the most general SU3 invariant gauge invariant Lagrangian allows this theta E dot B term. Since this CP variating, it can produce huge EDM if the parameter theta is order 1. So now we know that this theta must be smaller than 10 to minus 10. So then we have to understand why is that small. Of course, we can put small number, but this is not the answer we want to have. So the Petrov-Kim mechanism is, I think, probably the unique possibility of explaining this strong CP problem in a nice way. So the basic idea is that we put by hand some QCD anomalous global U1 symmetry, and we break it spontaneously. Then the Goldstone mode of this guy, the PQ charged singlet field, it couples to global duo like the theta term here. So now you know that the QCD condensate below 1 GeV, then this will generate the potential for this Goldstone boson in this way. So this develops some cosine function. Then here I didn't wrote down theta term. So and then actually since this is dynamical variable, the constant theta term can be observed into this dynamical field. Then you minimize it and you find that there is a minimum at A equal to 0. So theta has to be 0. So the strong CP problem can be resolved in this way. So this is very nice. Once you are willing to introduce QCD anomalous global U1 symmetry, well, in certain setup, it may be some automatic consequence of your more complicated gauge symmetry, higher gauge symmetry. Well, anyway. So there are typically two ways of realizing the Petrov-Kim symmetry. The first idea was put by Kim, and then Schiffman, Weinstein, Zakharov. So we assume some heavy quarks, so left-handed, right-handed. Well, I use the chiral rotation, and then introduce one Petrov-Kim charged singlet field. then here we can have an additional U1 symmetry under which these fields are charged like this. So obviously, it's left-handed and right-handed quarks have different charges, so that it is anomalous. And that's SU3. So here the SU3 quantum number is nothing but number of these QC quarks having charge -1. And another way is to extend the Higgs sector of the standard model. So typically in the 2Higgs double model, we can have additional U1 symmetry by allowing this S squared HU HD term. So here, this is another U1 symmetry allowed in this potential. And then as a consequence of that the 2 Higgs is charged under this Petrarchy symmetry, also the right-handed quarks. So here the QCD anomaly is just 2 times 2 coming from UC and DC, and number of generations is 6. So in fact, this QCD anomaly is nothing but domain wall number, which could cause some problem in cosmology. So now from the axion potential, we can calculate the axion mass, typically around 100 microelectron volt, taking the axion scale around 10 to 12 GeV. And then so you can also couple to photon, which is typically size of 10 to minus 15 over GeV. Of course, the detailed numbers for axion mass and A gamma coupling depends on the models. So this will be important to search axion astrophysically or cosmologically. And since axion, although axion couples to matter very, very weakly like this, but it can be produced sizably inside stars. So from star cooling process, we can put very strong limit on this axion scale, larger than 10 to 10 GeV. Okay, now, so Petrarchy symmetry was broken at high scale, say which is around 10 to 10 GeV. So this round value, there is a Goldstone mode. So it has a periodicity of 0 to 2 pi, the PQ breaking scale, right? And then below 1 GeV, the QCD condensate, and then there develops some non-trivial QCD vacuum for the axion. And then for this axion, the axion decay constant is actually the Petrarchy symmetry breaking scale divided by QCD anomaly, the domain null number. So in this QCD potential, the periodicity is just A from 0 to 2 pi FA, not 2 pi VPQ. So that since the VPQ is n, so integer number times FA, so there can be n different vector in this QCD potential. So this is exactly degenerate vector, and since we have degenerate vector, there could after QCD condensate, there could be domain walls produced in the early universe. So if domain number is larger than 1, I mean, there is danger to produce domain walls after QCD phase transition. So this has to be avoided. So any model, any axion model having domain wall number larger than 1 is potentially dangerous. So this is particularly the case if PQ symmetry is broken after inflation. So PQ symmetry is broken after inflation, you have to impose domain number to be 1. But the PQ symmetry can be broken during the inflation. So and then so domain walls inflate OA, so you don't have to worry about that. So in this case, you can accept any axion model having domain number larger than 1. But in this case, axion is very, very light. So typically much lighter than a Hubble parameter during the inflation. So that you can have huge fluctuation proportional to the Hawking temperature of the universe, the inflation period, namely the Hubble parameter. So you can contribute iso-curvature fluctuation today. So yeah, from this potential, the action can be initially misaligned, and then it can roll down to form the cold dark matter. So this is one contribution, and then there could be also this quantum fluctuation created during the inflation. So typically, we can have these two contributions in Axion CDM abundance. Okay, so here the theta is the misalignment of action field, and then this alpha topological defect counts the effect from the production of axionic strings and unstable domain worlds. So depending on different groups, this number can be either from 1 to 100. So now the most recent calculation by some Japanese group, well, they according to their calculation, alpha is typically order of 10. And then, okay, this is a quantum fluctuation produced during the inflation given by this size. So again, if PQ symmetry is broken during the inflation, which is applicable for domain low number larger than 1, then of course the theta is initial misalignment, so we don't have this topological defect effect, and then it's 1, and then there can be some sizable delta theta contribution given by this. So if PQ symmetry is broken after inflation, of course we don't have this delta theta term, and then this theta should be averaged over the initially allowed possible values. So typically this is about 6. And then again, this is the case for domain number 1. So from these two contributions, okay, so then, okay, so this is typical the action abundance depending on which period PQ symmetry is broken. So now, if dark matter is mainly composed of action, so we have to look for it. So actually, there are quite many experiments looking for actions or action-like particles. So as Yamas showed, here the main search channel is through A2 gamma gamma vortex. So this is a huge extension of parameter space for this coupling G A gamma gamma, and there are also huge ranges of action mass. So these two lines correspond to either KIAS-VG or the FSG CDM window. Then the rest is just action-like particle range. Right. So these are the current excluded region. Then this is the future sensitivity region searched by IAXO. And then if you remember, about 1 month ago, the XMM Newton announced, I mean, they made a big fuss about the discovery of actions, solar actions, which might be a dark matter candidate. So according to their paper, so this is their signal region, which is very close to the already excluded by KIAS. But this region, I mean, this is quite, but their analysis is quite, you know, I think actually the many experts didn't agree with their region. Also, it's very far from the cold dark matter region, but you know they made this media advertisement mentioning that they found cold dark matter action, so dark matter problem solved. So that's a kind of a rhetoric that went too far. Okay, anyway, okay, so then this is the ADMX excluded region, which is which covers only part, a very small region of CDM Axion window. So, so if we extend this region around, which is important in particular for us, between the micro electron volt to milli electron volt. So this ADMX excluded already this region, and then this is future sensitivity, this one and this one. And then, okay, so the CAP is new experiment in Korea. So actually, yeah, what they see is that we have this strong magnetic field inside the cavity, and then if CDM Axion pass through, then this B field will convert to, the Axion will convert to photon, so that you can amplify the signature of this micro electron volt or milli electron volt Axion, this photon signals. Well, this is the way to detect CDM Axion. So you need very strong magnetic field or high quality conversion, I mean the amplifier qualification to have a better sensitivity. So according to the leader of this group, so the CAP can cover this region if they build a nominal B field. So if they can improve the quality of this amplifier, then they can reach up to this. And then even stronger B field, they can go down like this. So this is, remember the Petraikin scale around 10 to 12 GeV, the actual mass was about 10 micro electron volt. And then the Axion window is then, in terms, okay, this is in terms of Axion mass. So Axion mass then should be between 10 micro electron volt to 1000 micro electron volt. The 1000 corresponds to FA rather than around 10 to 10 GeV, limited by the stellar evolution. So still, okay, so according to this, this CAP or ADMX can cover up to 100 micro electron volt. So here is KSVG or DFSG, and this is an Axion model. Yaman talked about 2 days ago. So yeah, I mean this CAP may find Axion in this area or in this area. Then I think that the 2 Koreans can get Nobel Prize, either Kim and CAP or An and CAP. So it's, I mean, Yaman, you should live long, maybe 100 years. Okay, so and there's also an interesting story about this having this strong B field in Korea. You know, the Korean government wasted a lot of money to realize artificial sun. You know, we have the so-called the nuclear fusion project called K-STAR. So there we needed a strong B field. So it seems that we already have good technology to build a strong B field. So the leader mentioned these K-STAR facilities, and then there is very good. Well, so far this is the field that we have in Korea now, but there is a good chance to have even to build a stronger field. So probably this K-STAR project is not totally useless. Okay, and then this is new ADMX future sensitivity, of course. Okay, so 2016 target is about up to about 50, 20, 30, or 40 micro electron volt. And then, of course, the CAP is more ambitious to cover around 100 micro electron volt. So they basically can prove KSVG and DFSG and ANS model is a bit away from ADMX. So I think, right? So you should be, yeah, you should be also really okay. Okay, so yeah, here's the main part. So after bicep 2, which may not be true, so many people, so a couple of groups reanalyzed the Axion, the constant on the Axion CDM window, assuming high scale inflation. So if bicep 2 is right, so the inflation Hubble parameter should be around 10 to 14 GeV. So considering this isochromature fluctuations during the inflation, I mean this lot of range, the parameter ranges are excluded. So if this is the right value for Hubble parameter during the inflation, so to have right Axion CDM, we have to sit in this particular point. So FA around, say, a few times 10 to 10 GeV. And below which the omega AH squared is smaller than 0.1. And then most likely the Petrarchian symmetry is broken after inflation, having FA is smaller than HI, so that the Domelo number 1 is required. Okay, so this is good news in a sense. Since it excluded a lot of Axion models and then a huge area of parameter space. So, but so myself and our Korean colleagues came to say opposite. Say, okay, so there are ways to evade this conventional constraint. So yeah, so here the one idea. I mean, this is not a new idea. It's quite well known for many years. So the PQ breaking scale during the inflation may not have to be the same as the PQ scale at the present time. So this can be time dependent. So that if FA during the inflation is much larger than the present value, the isochromature perturbation can be suppressed enough. Okay, if this is not enough, at the later time, you can have, say, another inflation period. It's called the thermal inflation. And then at that time, the QCD scale can be much larger than the present value, which is around 0.4 GeV. So in that way, we can have different Axion potential during this second inflation period. So this can also erase out all the isochromature perturbation. So if this is, okay, so if FA during the inflation is large enough, you can completely erase out the isochromature fluctuation, or later time you can achieve these two. So so this is still work in progress. So first idea is that okay, so basically we just assume that during the inflation the Petrarchian scale is different from our current value. Then from the previous indication, you can just look for how large the PQ scale during the inflation you have to have. So in order to have omega AH scale around 0.1, so this window is just allowed. So depending on the presence of FA, say from say 10 to around 10 to 11 to 10 to 12, 13, 14 GeV, so the Petrarchian scale during the inflation should be closer to Planck scale and then 100 times Planck scale. So you may not like this trans-Planckian value for PQ scale. Then if you stick to the PQ scale during the inflation smaller than Planck scale, so you end up with having very suppressed omega H scale. So say much below the required amount. So in order to have a sizable Axion CDM, I mean, you need to accept trans-Planckian PQ scale during the inflation. So it may not be too bad because we know the most inflation model is trans-Planckian values for inflation field. Okay, so supersymmetry break. I mean, in order to motivate the time-dependent PQ scale, let us remind the Suji breaking caused by inflation. So to have inflation, we need some scalar field chi, and then if we have supersymmetry, say for quarks represented by phi or leptons, and then we have to allow this generic potential, the Keller term like this. But the having inflation with a large Hubble parameter h means that there is such energy density given by this VEF. So then this will generate Suji breaking mass to this quark or lepton field. So if this sign is negative, then it can give, say, large negative soft breaking mass, so that you can develop a huge web for this phi. So we can apply this idea. So basically the idea is that this phi is a PQ symmetry breaking scale. So we allow this higher dimensional potential to have very, very flat potential. And then during the inflation, we can have Suji breaking effect by inflation proportional to Hubble parameter. It's the A term is proportional to H, and mass term should be H squared. And then after inflation at present, of course, this term goes away. Then we have the usual soft parameters denoted by A or M phi squared. So in this way, during the inflation, so minimizing this, we can have, okay, so for, at present time, the minimum of this phi is determined by the usual Suji breaking scale times Planck mass to the power of 1 over, say, n+1. So in this way, we can generate intermediate scale PQ symmetry breaking scale as some geometric mean of TeV scale Suji breaking times Planck scale. So this is one of the natural way to generate this new scale PQ symmetry breaking. And then during the inflation, the same mechanism works, but with a much larger Suji breaking effect. So then the PQ scale during the inflation can be much larger than the present value this way. So for this work, of course, the PQ symmetry shouldn't be restored throughout the history of the universe. So once it's restored during the radiation dominated era, then you have to have domain number 1. So basically, the reason why we think of this possibility is that we want to allow any action model which has a domain number less than 1. And then stronger QCD. Okay, so now so we can have some thermal inflation along the Higgs direction. So now, so imagine to have this high dimensional operators like HU or HD squared, which has dimension 4 in the superpotential, or LHU squared. So then this Higgs field or lepton field can have thermal mass squared and a negative usual soft mass squared. 10 minutes. Okay. No. Including ski. Okay, then I should stop here. Okay, give it 5 more minutes. Okay, then the temperature rather than say TeV scale soft parameter, the vacuum, the potential shape is this, and then if T becomes below M, and then potential, there is a new true vacuum for phi far away from the origin. So as temperature become smaller, then we can have this kind of phase transition. So this is nothing but, this is the old thermal inflation idea applied to originally to the inflation at the end, in the beginning of the universe. But now, okay, so having this structure, we can have, say, inflation at after the short period of thermal inflation after the original inflation. Then at that time, this vacuum value is nothing but the 5F squared is soft mass squared. So the whole parameter is given by this size. So typically having the TeV scale soft breaking mass, and then the 5F around 10 to 10 GeV, we have inflation, the Hubble parameter during the thermal inflation around 10 to minus 6 GeV. Okay, so then now this this flaton, say, now in this case Higgs field or lepton field can decay, of course, after this thermal inflation to reheat the universe around say 10 GeV, taking usually again the typical values. Then it will produce a lot of entropy, so you can dilute away any pre-existing relics, including the axionic isochromatic fluctuation. So here again, the dilution factor is 10 to 14 GeV, which is huge enough. Then the idea here is that during the thermal inflation, the Higgs wave is much larger than, say, the current value. So, I mean, this can be easily 10 to 10 GeV. Then the QCD can be even stronger than the present value. So here, if the Higgs wave is much larger than, say, TeV, then we have, the ordinary quarks become much heavier than the present value. So we will have different evolution of QCD alpha parameter. So we evaluate this evolution of RG evolution of QCD alpha parameter, and then one can calculate, say, taking the this Higgs wave from, say, 174 GeV to, say, 10 to 10 GeV. The lambda QCD can vary from the usual value of 0.1 GeV to, say, TeV. So during thermal inflation, the lambda QCD can be around, let's say, TeV region. So this is particularly interesting. So in this case, we have to recalculate the axion mass. So and then lambda QCD is around, say, TeV. And then the axion potential is different from the present value. So typically in this period, axion mass is around 10 to minus 4 GeV. And then of course, in order not to regenerate the isochromatic perturbation, we need to impose the axion mass during thermal inflation is much larger than the whole parameter during thermal inflation. Okay, sorry, physics is more important than skill. Okay, so in this way we can avoid the dangerous size of fluctuation perturbation. So now I come to the end of this first part. Okay, so Axion is a good Dagmar candidate solving a strong CP problem. But if the inflation is done by high scale, I mean high scale inflation is right, then we have very strong limit on the conventional standard cosmology. However, so we can have some other ways to avoid this problem. So I presented two ideas. So, and then, yeah, Cheng Hei gave me a few more minutes to basically thank to him and NCTS members. Yeah, I really appreciate their effort. Actually, the Professor Xia Gang Ho brought to life the dormant KIAS-NCTS MOU. So he told me that after he became the leader of NCTS, he looked back to the old document and found the MOU between KIAS and NCTS back to, I don't know, 1998 or 9. So somebody signed, then forgot. I didn't know. But then he said, oh, why not having this MOU again and activate our collaboration? So yeah, at the time I was a chairman of physics department, so okay, let's do that. So then this is the starting point of this bloody KIAS-NCTS joint workshop. And then, okay, last year we had the first joint workshop in beautiful ski resort in Korea. And then Changhae organized this nice workshop here. And then actually, originally I was gonna make some complaint about the too tight schedule, but it was totally covered by a wonderful banquet yesterday. So I didn't put any word. Okay, so basically we should continue closer and broader collaboration in the future. So in order to have that, so we decided to have a third KIAS-NCTS meeting at Taiwan again in 2016. So I hope many of NCTS members will attend. Of course, other people are welcome to join. And then this next January, there is another Taiwan workshop. Also, NCTS is supposed to participate. It's not official joint workshop, but NCTS also support morally. And then again, I mean, unfortunately, this is from January 25th to 31st, which I learned that complete overlap with the annual NCTS meeting.
No. Annual meeting of Physics Society in Taiwan.
Oh, that's okay.
Not just NCTS.
All right. You know, in Korea, we usually don't go to the Physics Society meeting. Okay, so, and actually, if you didn't hear about this, probably Cheng Chiang was afraid of announcing it officially. So, but you know, I announced it secretly only here. So if you can escape from this beautiful annual meeting of Taiwan Physical Society meeting, please come to Taiwan. I mean, this is really a nice ski resort. And then, so with just the $10, you can ski one day. It's very cheap, and then you can enjoy also nice food, and then also physics. Okay, thank you very much.